Welcome to today's Explainer. If you're working in neuroscience, EEG engineering, or building BCIs, you know exactly how absolutely critical signal purity is to our work. We're diving into a groundbreaking architectural leap in electroencephalography preprocessing. Specifically, we're going to unpack a performance-shattering denoising pipeline that directly solves one of the most persistent hurdles in continuous brain signal recording.
Here's what we're looking at today: the EOG artifact problem, introducing MWC-GAN, the wavelet-domain difference, some unprecedented denoising results, and finally, advancing BCI and clinical EEG. Let's jump right into part 1, the EORT artifact problem.
Look, we're all deeply familiar with this struggle, right? When you're dealing with continuous EEG, those non-stationary electrooculography signals, especially involuntary eye movements and blinks, are incredibly difficult to separate from the underlying neural activity. It's a persistent bottleneck that completely wreaks havoc on downstream analysis. Whether you're classifying intricate motor imagery tasks, identifying P300 spellers, or running continuous cognitive workload monitoring in high-stakes environments, this is the hurdle. The real nightmare here is that EOG artifacts predominantly occupy the 0.5 to 12 Hz frequency range. They directly overlap with vital task-relevant signals, like the delta and alpha bands. Because these artifacts are non-stationary and carry much higher amplitudes than the actual EEG, your traditional time domain approaches, like simple notch or bandpass filters, end up totally distorting the crucial spectral data. Sure, you might remove the artifact, but you sacrifice the spectral fidelity of the brain signal in the process. It renders the data practically useless for delicate frequency-based decoding.
Okay, part 2, introducing MWC-GAN.
Enter the MWC-GAN. This is an incredibly elegant, hybrid multiscale wavelet-domain conditional generative adversarial network. It completely abandons the pure time-domain black box approach. Instead, it operates entirely within the wavelet domain. By processing decomposed wavelet coefficients, it explicitly captures both the local waveform morphology and the long-range temporal dependencies of the signal. Following the pipeline, the process starts by converting the raw EEG into wavelet streams. These noisy and clean wavelets actually serve as conditional inputs to the network. The generator block uses a hybrid separable convolutional neural network paired seamlessly with a temporal multi-head attention mechanism. The output then hits the wavelet conditional discriminator, which uses an explicit adversarial feature matching objective. This guarantees the generated output perfectly matches the expected temporal and spectral structure of clean neural activity.
Moving on to part 3. The wavelet-domain difference. So, what's the fundamental difference here? Well, pure time-domain models just lack an explicit joint time-frequency representation. They're often constrained by finite receptive fields, which means they really struggle with slowly varying long-range ocular artifacts, ultimately causing a severe loss of spectral fidelity. The MWC-GAN multiscale wavelet approach, on the other hand, acts as a learned wavelet-domain filter bank. It captures both local and global dependencies, and through that explicit adversarial feature matching, it rigidly enforces the preservation of those highly vulnerable low-frequency spectral characteristics.
Let's break down the generator's precise operational pathway. Step 1. The signal gets decomposed using Adabaki's 4, or DB4, wavelet filter bank, breaking it into multi-resolution wavelet coefficient vectors. Step 2. These vectors pass through a separable CNN, utilizing depth-wise separable convolutions to extract localized, band-limited temporal patterns, literally isolating the artifact's unique morphology. Step 3. It feeds into a temporal multi-head attention encoder to elegantly model long-range cross-channel dependencies. And finally, step 4. The denoise coefficients are perfectly reconstructed back into a continuous signal via the inverse discrete wavelet transform. It's an incredibly optimized pathway.
Which brings us to part 4, unprecedented denoising results. The MWC-GAN hits a record-setting average signal-to-noise ratio of 13.97 decibels. For context, this definitively proves that the network suppresses residual EOG noise way more effectively than previous standards, all while maximizing the amplitude preservation of the underlying clean signal across the board. When you look at the complete performance picture, it's pretty staggering. Benchmarked against traditional EMD CCA and leading networks like GCDNet, Novel CNN, and Simple CNN, the MWC-GAN absolutely dominates. Alongside that 13.97 dB SNR, it yields the absolute lowest time domain and frequency domain relative root mean square errors recorded on the dataset.
We're talking a time domain error of just 0.2599 and a frequency domain error of 0.2832. This isn't just an incremental update. It's a definitive structural advantage over pure convolutional neural network baselines that notoriously strip away the exact signals we're trying to decode. The time domain data really shows the precision. There's a highly contaminated, noisy signal with a massive EOG spike in red and the clean ground truth in black. Now tracking the denoise signal in blue, notice how it follows the ground truth flawlessly. It perfectly isolates and strips out that high-amplitude artifact without flattening or distorting the underlying microfluctuations of the neural data. The morphology is just immaculately preserved.
And crucially, for any real-world engineering application, the power spectral density charts prove this unmatched spectral fidelity across all frequency bands. Notice that extreme low frequency range on the left, that notoriously tricky 0 to 12 Hz band. The denoised MWC-GAN output in blue hugs the clean ground truth in black incredibly closely. It completely avoids the signal loss and spectral distortion that we've come to expect from older time domain baselines.
Finally, Part 5. Advancing BCI and clinical EEG. By successfully locking in both the temporal structure and spectral characteristics of the underlying neural activity, MWC-GAN is really emerging as the ultimate preprocessing tool. Because it doesn't even require a dedicated reference channel for eye movements, it enables automated end-to-end continuous operation. This is genuinely transformative for motor imagery brain-computer interfaces, high-fidelity cognitive workload monitoring, and uncompromised clinical EEG assessments. It cleans the data without destroying the subtle signatures you're actually trying to decode. So given this unprecedented leap in spectral preservation and morphological accuracy, think about your current workflows. How will integrating this exact multiscale wavelet-domain conditional architecture elevate the accuracy of your own hardware setups and research pipelines? The standard for pre-processing has officially shifted, and it's time to leverage this structural advantage in your next build. Thanks for joining us for this explainer.